Hi there, my name is Vernon Wetzell. This video is a quick overview of the research that I'm doing with the help of my advisor, Dr. Adrian Kuhl, in the Department of Physics and Astronomy at San Francisco State University. This project can be briefly described as a long look at M12 X-rays, but there's quite a bit more to it, and we'll get to that in just a moment. Before we get started, I wanted to give a short summary of what we'll talk about in this video. We will first talk about M12, what it is, where it is, etc. We'll then talk about the data we're using and where it came from. Once we know what data we're dealing with, we're going to look at how we are going to identify and characterize sources within this data. We will follow this up by looking at some other studies being conducted on M12, and finish up with the significance of this work and the next steps that need to be taken to finish this project. Now we can dive in. Messier 12, or M12, or NGC 6218, is a globular star cluster. Globular star clusters are densely packed clusters of tens of thousands up to millions of stars that orbit the Milky Way galaxy. M12 is roughly 15.7 thousand light years away and contains about 87,000 solar masses. Another important measure of a globular star cluster is something called the half-light radius. This is the radius in which about half of the light from the cluster is emitted. For M12, the half-light radius is about 2 arc minutes. If you want to go outside and see M12 for yourself, you can see it during the summer months in the constellation of Ophiuchus on a clear dark night with a good pair of binoculars. For our research, we used an instrument that's a little bit more powerful than a pair of binoculars. The data we are using was taken using the Chandra X-ray Observatory, which you can see in the bottom of the slide. This is the X-ray equivalent of the Hubble Space Telescope. In total, our data is comprised of 8 observations, which add up to a total exposure time of about 2.5 days on the ACES-S detector. After all that time, however, we only received a few X-rays from the sources within M12. The merged data is shown below me. The inner blue circle is the half-light radius, and the outer blue circle is twice the half-light radius. As far as X-ray data goes, this is a pretty deep and clean image, but now we have to analyze it. To do this analysis, we are using a software package called Chow. This package was specifically designed to make sense of raw Chandra observations. In particular, for source detection, we use a tool called WaveDetect. This tool finds sources by correlating our image with a Mexican hat model. Below me again, you can see the same image as before, but now with our source regions circled in green. Once the source regions are identified, WaveDetect estimates certain properties of those sources, such as the flux, or the amount of X-rays that those sources give off. We are currently in the process of finalizing our source list, and once that is complete, we will be able to move on to source characterization. We will be characterizing our sources using several different methods. One particular way in which we will characterize the sources of M12 is by looking at them on an X-ray color magnitude diagram. This will appear similar to the plot directly below me, which is an X-ray color magnitude diagram of the globular cluster 47 Tukh. One important note with these color magnitude diagrams is that the color is defined as the difference in brightness of a source between two different energy bands or wavelengths of light, and the magnitude is the overall brightness of that source. Based on the positions of our sources on this plot, we will gain insight into the physical mechanisms that are emitting X-rays from our sources in M12. Unfortunately, it's difficult to pin down exactly what is emitting the X-rays from our data alone. This is where studies in other parts of the electromagnetic spectrum come into play. There are 3 main spectral regimes of interest when it comes to source characterization. The first is visible light, what we see every day. The instrument we use to study this is the Hubble Space Telescope. Using Hubble, we are more precisely able to locate sources, and using the source's spectra, we are able to pin down what we think the underlying phenomena are. An example of a Hubble observation used to locate X-ray sources is shown below me, with the same blue half-light radius circle and green X-ray source regions as earlier. The next spectral region are radio waves. This is being done primarily with the Maverick survey. Radio waves allow us to identify sources with extreme accuracy, in particular millisecond pulsars. The final spectral region are gamma rays. These are extremely high energy emissions which can only be created in and around extreme sources. Part of the motivation for this X-ray survey was driven by gamma rays detected coming from the direction of M12 using the Fermi Gamma Ray Space Telescope. Now we turn to the real important questions, though. Who cares? Well, for one, I do. But aside from me, there's a large portion of the physics and astronomy community that this research benefits. One group that this research contributes to are the high-energy physicists and astronomers. There are not many phenomena in the universe that have the energy required to emit X-rays, and the few that do push the limits of our understanding of physics. The high density of stars and globular clusters leads to a concentration of these high-energy phenomena. Some examples of these include millisecond pulsars, quiescent low-mass X-ray binaries, cataclysmic variables, and several others. Another group that this work will interest in the near future are gravitational wave astronomers. Many X-ray emitting phenomena are compact binary systems, which will eventually lead to gravitational wave events when they merge. Being able to identify these binaries before they merge will be invaluable in the study of gravitational radiation. And with that, we'll bring it back to the project at hand. To finish this project out, we will start by finalizing our source list. Once this is complete, we will inspect our sources, analyzing their energy, their magnitude, and their spectra. And we will complete our work by passing our findings along to researchers working with other instruments in the form of a peer-reviewed paper. If you have any questions or would like to know more about the research we are doing, there will be a Q&A session on Thursday, March 4th at 4 p.m. at the Zoom link below. If you are unable to attend but have questions, please feel free to email me at the address below. I hope you enjoyed this summary of my work with the X-rays of M12. Thank you so much for your time.